Good morning, dear students. Today we are going to discuss about topicity, an important topic in stereochemistry. As we learn this topicity, you will understand different type of ligands and different type of phases that each ligand is having. And in topicity, we are also going to learn anisotrophic and diastereotopic molecules. So actually, what is this topicity? What is the main definition of this topicity? In topicity, the first things what we are going to cover is, the first one is, you are going to learn what is homotopic ligands or homomorphic ligands. Okay, so as I cover each topic, I will cover each topic with explanations and examples. Rest of the examples make sure that you will do from PG Pathashala or some other described textbooks. Not degree portions or PG portions textbooks, but the textbooks for the PG students only you have to go through, because in the degree portions these theory or these examples are not there. So the first thing what we are going to learn is homotopicity. Homotopicity. Okay. Now as the term homo means equal, you know that. Homotopicity, the other name is homomorphic ligands. They are also known as the homomorphic ligands. Homomorphic ligands, when we say homo, that means it is a Greek word. It is a Greek word meaning same. Meaning same. And morphism, these words we have discussed a long time before for different things. So the moment I began stereochemistry, these terms are familiar to you. Homo means same, morphism means form. Same form. Now, whenever we were saying stereochemistry, we always consider the example of carbon. Carbon is attached to 4 different molecules. Then we call that carbon as an asymmetric carbon. And if the two ligands can exchange their phases, or two molecules can interchange and they create or they give rise to a different type of isomerism, that is called stereoisomerism or stereogenic center, asymmetric center. So whenever I am teaching you these things, please remember that you will keep behind your mind all these topics. Okay, so what is this homomorphic ligands? For example, let us consider an example of carbon having attached to 4 different groups. That is, one is an acid, another one is an hydrogen, and another one is a methyl group. Again, you attach this carbon to another hydrogen. Okay, now what happens? The hydrogen which is attached to the central metal of carbon, to the central carbon, there is 2 hydrogens. This carbon is not a stereogenic center. Now itself you will understand that two apparently identical ligands in a molecule are called homomorphic. The hydrogen, for our easy sake, we will name it as an HA and HB. They are identical ligands. So when a carbon is attached to two identical ligands are called homomorphic ligands. The relationship between the two hydrogen atom, the relationship between the HA and HB in connection with the entire molecule. The relationship between HA and HB with respect to this entire molecule is called a topic relationship or topicity. Okay, HA individually cannot be related to this molecule. HB individually cannot relate to this molecule. But the relationship between HA and HB with respect to this entire molecule only will give you the word topicity. Topicity. Okay, now another one is homotopic ligands. What is this homotopic ligands or homotopicity? Topicity describes the relationship between the two ligands with respect to the molecule. Now let us consider an example that, suppose you have homotopicity. Okay, consider central metal atom carbon is attached to four different groups: HC, HA and HB. All of us know that the relationship between the HA and HB and HB and HC with respect to this central metal or central atom carbon is called topicity. Now we will consider why these ligands are equal in phases. Now let us replace HA by fluoride. Let us replace HA by fluoride. Now what happens to this molecule? You have carbon, chloride, HC remains as it is, HB, and you have HA is replaced by fluoride. Now replace same way HB by fluoride. Chloride, HC, HA and fluoride. Now the position is different. The position of the fluoride ion with respect to the above molecule is different. But you can interchange these groups. Stereochemistry I explained to you by interconverting twice the molecule or the groups around a central carbon atom. We will get the same configuration. So here you have fluoride. Here HA comes, here HC comes. Can you see these two are identical? Now same way replace another important molecule group here, that is HC. When you replace here, HC is replaced by fluoride. HC is replaced by fluoride. You have HB and HA. Again you can see the position of the fluoride ion from the above molecule is different. But you can interconvert these groups. You can interconvert this group twice. Then you will have HA, HB and fluoride. These three are identical. That's why this is called homotopicity or homomorphic ligands. All three molecules with no chiral center. There is no chiral center for these molecules. So they are called homotopic ligands. A simple example is what I have taken here. Okay, but you please remember that instead of hydrogen, HA and HB, HC, if you are having different groups also, we should be able to identify this homotopicity or homomorphic phases. For example, let us consider another example such as you have again bromide, HB and HA. Can you make out this is a topicity? The relationship of HA and HB with respect to this molecule is a topicity. The relationship between a bromine and second bromine with respect to this entire molecule is topicity. And they are also homomorphic. Now we are going to prove that they are not only having a topicity in nature, but they are also homomorphic in case. Okay, so HA can be replaced by X. Imagine. Okay, now what happens? You draw the molecule, bromide, HB, and you have your X. Now HB you please replace by X. Again you have bromide above. Below the plane bromide is there. HB, HA. Can you see the difference in this structure? They are not chiral, but only by interchanging these two groups you will have a same structure in the molecule. So there is no chiral center, and they are homomorphic. So these are called homomorphic ligands. Ligands by itself or ligand by itself, when they are present in a group, you cannot say they are homotopic. But ligands, when they are present in a molecule with no chiral center, but replacing one group with another group will give you a same stereochemistry or stereoisomerism. That's why it is called a homomorphic ligands. Now, instead of having these general examples, let me give you an example with our groups, like acid groups, bromine groups, halogen groups. Because now, whenever I say HA, HB, if you are not able to identify with the different groups, again the homomorphic, you will get a confusion. Okay, so you have here one acid group, again an alcohol, OH group. Now double stereogenic center is there, HB. Again you have an acid group here. Again you have HA and OH. All of us know that there are two stereogenic centers, so it will give rise to 2 raised to 2, 4 stereoisomer. That you think your basics are thorough. So I am thinking that you are thorough with your basics. Now HA should be replaced by deuterium. All of you know that hydrogen isomer of the hydrogen is the deuterium. So replace this HA by deuterium and draw the molecule. You have acid group, OH group and deuterium. HB here HOCOOH. Now again replace HB by deuterium. HB by deuterium. Again when you write here the molecule is COH, OH, HA, OH, deuterium COOH. Now what happens? Now by interchanging, by rotating one molecule, if you name it this A and name it this B, okay, either rotate molecule B with respect to A or rotate molecule A with respect to B for 180 degrees. For 180 degrees. Then what you get is an identical molecule. You get an identical molecule and that identical molecule is called homomorphic. Homomorphic ligand or homomorphic topicity. Okay. Now we are going to discuss next thing is heterotopicity. What is this hetero? Now when I say homomorphicity or homomorphism, automatically you will be able to understand just the opposite will be the heterotopicity. But I will teach you. Now next thing is heterotopicity. Heterotopicity. Homomorphic groups must be identical. In the above cases you have seen HA, HB, bromine, bromine, bromide, bromide, again COH group, again HA and HB. Though for us easy to understand, we named one hydrogen as HA and another hydrogen as HB. But in reality, hydrogens are same. Hydrogens are same. No hydrogen A, no hydrogen B. Okay. So that is why they are called homomorphic. But in heterotopic, homomorphic groups must be identical and must have a same constitution and a configuration. But whereas in a heterotopicity, it is not necessary that groups should be identical. Groups should be identical. For example, you consider a molecule. Okay. Now we are going to a complex structures. Okay, benzene having, then behind the plane of the plane you have one OH group. Again here behind the plane only one methyl group. Above the plane of the paper, you know, dashed wedged and thick wedged when we write, you know, one will be the behind the molecule and another one will be above the plane of the molecule. Okay, so what happens here? Heterotopicity. These are here identical, but their configuration or their stereochemistry, the relative configuration can be different. Okay, so here it is an R and here it is an R. Here, but it is behind the plane of the paper. This methyl group is behind the plane of the paper, whereas this methyl group is above the plane of the paper. But the same stereo center are here also are configuration only, but the position is different. The position is different. For example, you take another molecule. Okay, suppose you have here CH3. Again, above the plane of the paper, you have a chloride, one eno group. Again, you have again above the plane of the paper, one chloride, again CH3. Okay, here though they both chloride atoms are above the plane of the molecule, the configuration is one, it is S configuration, and another one is R configuration. Groups are identical, constitutionally similar, but they are not configurationally identical. Okay, constitutionally both, in this case both are methyl groups, but configurationally also they can be identical. But what happens here? They are constitutionally identical, but configurationally they are different. So they are not homomorphic. They are not homomorphic. They are heterotopic. They are heterotopic. There is another way to identify the ligands whether they are homotopic, that is through their symmetry criteria. Okay, all of you have learned symmetry. Group theory you have learned, in that you have seen CN axis. Okay, center of symmetry, identical axis, inversion, reflection. Okay, now through the symmetry also you can identify whether a molecule is, whether the ligands are homomorphic in nature or a heterotopic in nature. So based on the symmetry criteria we will be explaining, based on the symmetry criteria. I am very sure that Miss has already taught you symmetry. Thinking that you are thorough with your symmetry only, I am not going details. So if the molecules are containing CN axis, if a molecule contains a CN axis, by the rotation of that CN axis, if we can interchange the ligands by the CN, we will call it as homotopic ligands. Okay, through the molecule, by having rotation through CN axis, rotation through a CN axis, if you get a same molecule like the previous one, then you call it as a homotopic ligands. So let us see what is the example here. Here you have one methyl group, CH3 above the plane of the paper. You have hydrogen along the plane of the paper or along the plane of the molecule. Again you have hydrogen. Again another methyl group is below the plane of the paper. Below the plane of the paper. And the CN axis, all of us know, it is a center of inversion, goes along the center of the molecule. Along the center of the molecule. If you rotate this molecule along the CN axis, what do you get here? There is an interchange of these CH3 groups. So here you get CH3. Let me draw a different color of CH3 here. It is a CH3. Okay. For you, it is CH3. Now what happens here? You get here CH3 is, the blue color CH3 is coming above the plane of the paper, isn't it? Whereas this hydrogen remains same, and the black CH3 goes behind the plane of the paper. Behind the plane of the paper. There are same molecule. It is the same molecule. But if you get a molecule through the symmetry criteria, that if you rotate a molecule through CN axis, if you get an identical molecule same as the previous one, then it you call it as a homomorphic or homotopic ligands. They are homotopic ligands. Now, for example, if you take another molecule, you have one ethylene, CH, acetylene groups, sorry, that is HB, and you have HA, you have HA, then you have here CH3, then you have again here CH3, CH3. Again you rotate the molecule, there is a CN axis, isn't it? There is a CN axis. Rotate this molecule. What happens is you get here an interconversion. The CH3 molecule, black one goes here, and you get the red CH3 this side. Then you have a molecule HB this side, HA this side. Atoms or groups, when they are replaced, atoms or groups, when they are replaced with the different atoms or groups, that are not present in the molecule gives the same molecule, On rotation around the CN axis, the groups which are above the plane goes behind the plane, and those groups which are behind the plane comes above the plane of the paper. The structure is identical, hence they are homotopic ligands. Homotopic atoms or groups cannot be differentiated by NMR spectra. Okay, this is the homotopicity. This is the homotopic ligand homomorphism, and homotopic topicity is the different things what we have discussed now so far.